Space, the final frontier. Well, to this day it is not really clear whether space has a final frontier or is an infinite expanse. But what we can say for sure today is that our universe has a finite age. It is about 13.8 billion years old. And if the universe also has a spatial end, then its extent is much, much greater than the distance that light can travel in 13.8 billion years. But this current picture of our universe, that there is much more space than time, can lead to real challenges when modeling our universe. To approach this challenge, first a short excursion into signal processing. Here you can see an audio file that has been loaded into an audio editor. It's a very short file, it's only 1 second long. Does the length of the file have any effect on the content? Yes, it does. Basically, you can say that the frequency resolution of a signal depends on its duration. The less time we have to measure a signal, the less accurate the frequencies we measure in it will be. To determine a frequency of 1 Hz, the signal must be measured for at least 1 second. For our audio file, this means that the frequencies in the short sound cannot be distinguished more precisely than 1 Hz. For a normal human ear, this frequency difference is not audible, but there are applications in signal processing where the shortness of the measurement time can become problematic. The fact that measurement time delta t and frequency resolution delta f together cannot become arbitrarily small was first formulated by electrical engineer Karl Kupfmüller in 1924. 3 years later, the well-known physicist Werner Heisenberg formulated this relationship even more generally and also found the theoretical lower limit for the product of these two uncertainties, 1 divided by 4 pi. Since the beginning of the 20th century, it has also been clear that there is a fundamental relationship between the frequency of radiation and its energy. This relationship is therefore also known as the energy-time uncertainty relation and is fundamental to quantum mechanics, which is used to model our subatomic world. This is because in the world of the very smallest particles, short periods of time are common for certain processes and therefore also frequency inaccuracies. But now back to the original observation that our universe obviously has more space than time. As I said, our universe almost certainly has a finite age of around 13.8 billion years. And now it should be clear, no audio file, no process, and no oscillation can last longer than 13.8 billion years. This is the absolute upper limit for our delta t in the uncertainty principle. This means that there is also an absolute minimum frequency resolution. The formula for Heisenberg's uncertainty principle results in the best possible frequency resolution of around 10 to the power of negative 19 Hz for a universe with an age of 13.8 billion years. This is therefore also the best possible accuracy for the lowest frequency gravitational wave in the universe, which has a period equal to the age of the universe. The second lowest gravitational wave then has twice the inaccuracy, the fifth lowest has 5 times the inaccuracy and so on. For cosmic scales, this results in damn small inaccuracy values. And you might think that's the end of the matter, because such small uncertainties have no further influence on the physics of our universe. That could also be the case. But now we have to add what was already mentioned. We have more space than time in our universe. All current models assume that our universe has a much, much larger expansion than twice the distance that light travels in 13.8 billion years. If the universe is spatially finite, it is at least 250 times larger than the part we can observe. This means that there are many more wavelength values or wavenumber values than frequency values in our universe. The following diagram illustrates this fact. We have a much better wavenumber resolution than frequency resolution. This means that we cannot simply take a frequency for almost all wave numbers, with which the quotient is formed in order to obtain the value of the speed of light. Instead, we also get an inaccuracy for the speed of propagation. And this means something that is actually strictly forbidden in all current models of modern physics. Light propagates at different speeds depending on its wavelength. There is a term for this situation, dispersion. And now perhaps one of you will say, but there is such a thing, we can only see the colors of the rainbow through dispersion. That's true. But for this you need two media with different densities, for example air and water. But this formula here says, dispersion occurs in a vacuum. And now I'm sure there are more of you who are saying, if such dispersion exists in a vacuum, then it would have been measured long ago. Let's take a look at the propagation velocity inaccuracies for different wavelengths according to the equation. You can see that even for long-wave electromagnetic waves, such as those from long-wave broadcasting, there are inaccuracy values for the speed of propagation that are practically impossible to measure. Gravitational waves are therefore interesting. It can be said that gravitational waves are usually much longer than electromagnetic waves. These waves were also predicted by Einstein, and most physicists are convinced that they have now been detected by the LIGO laser interferometer system. Unfortunately, after initial reports of success in the first few years of its operation, LIGO has become rather quiet. Nevertheless, let's take a closer look at the success stories from this initial phase. The gravitational wave event GW170817 stands out in particular. On August 17, 2017, an event 130 million light-years away is said to have been successfully detected, in which the collision of two neutron stars emitted both extremely short wavelength gamma rays and long wavelength gravitational waves. The wavelength of the gravitational wave reached down to 10,000 kilometers. At this wavelength, our equation predicts a velocity difference of 1,830 nanometers per second. With a travel time of 130 million years, this means that the slightly faster gamma rays were able to catch up by about 7,500 meters, i.e. reduce the difference in travel time by 0.000025 seconds. Such a difference is not measurable. So we have to wait for gravitational waves with an even greater wavelength to be detected at some point. This project should succeed sometime in the 2030s with the planned LISA detector, in which the detectors are sufficiently far apart because they are stationed in space. We can look forward to it. There are already papers in which suggestions are made as to how the speed of gravitational waves can be determined using the LISA data. Another approach is to wait for long-term observations of pulsars to provide not only clear evidence of gravitational waves but also the magnitude of their propagation speeds. With the statement that gravitational waves do not have a continuous frequency spectrum, but can only be assigned to discrete frequency values, which results in large propagation speed uncertainties, especially at wavelengths in the cosmic range, we deviate from the assumptions of the general theory of relativity. However, this does not mean that the entire theory is called into question. On the contrary, it merely adds a correction that only has an effect at galactic distances anyway. In particular, we are now making use of an important finding of the general theory of relativity. The period of the dominant gravitational wave is exactly half of the orbital period that a celestial body needs when orbiting the center of gravity. In addition to this dominant gravitational radiation, there are also gravitational waves with higher frequencies, especially in very eccentric orbits, but it is an acceptable simplification in order to show in principle that there is a fundamental constant acceleration, which must lie approximately at 10 to the power of -10 meters per square second, and for ideal circular orbits even lies exactly at this value. This fixed coupling of gravitational wave frequency and orbital frequency of celestial bodies means that all orbital frequencies of celestial bodies are also fixed in a discrete set of values that depend on the age of the universe. For each orbital frequency, an inaccuracy is added up that corresponds exactly to twice the inaccuracy of the associated dominant gravitational frequency. Analogous to the frequency inaccuracy, we can therefore determine a minimum inaccuracy of all orbital velocities in the universe. This connection becomes particularly clear when you realize that every nth orbit class has a theoretical orbit in which the orbiting body moves at, almost, the speed of light. The length of its orbit must therefore be twice as long as the wavelength of its associated gravitational wave. This means that the rate at which its speed gains in accuracy is the same as that of its dominant gravitational wave, which, with a period twice as long, also means twice the speed in accuracy. This finally results in delta v orbit equals c divided by 2 pi n. The radial acceleration results from the product of the orbital angular velocity and the orbital velocity. The product of their two inaccuracies is therefore the inaccuracy of the radial acceleration. Here we now use the equations just established for delta omega and for delta v. This finally results in delta A equals c divided 2 pi t, universe, for all orbital classes n. So the decisive factor is: with increasing orbital frequencies, decreasing orbital periods, the inaccuracy of the orbital frequency also increases, but the inaccuracy of the orbital velocity decreases to the same extent. The inaccuracy of the radial acceleration, which is a product of orbital frequency inaccuracy and orbital velocity inaccuracy, therefore remains the same for all possible orbits. There is therefore a fundamental acceleration inaccuracy of about 10 to the power of -10 meters per square second. And this applies to all rotations from the cosmic down to the subatomic range. But especially in the cosmic range, in the order of magnitude of galaxies and beyond, it leads to phenomena that cannot be explained by either Newtonian mechanics or Einstein's theory of relativity. Galaxies rotate faster than Newton or Einstein would expect. Back in the 1980s, the Israeli physicist Milgrom established that for most observed galaxies, the deviation between the expected rotation curve and the actually measured rotation curve occurs at an acceleration of around 1.2 times 10 to the power of -10 meters per second. From this observation, he developed the theory of modified Newtonian dynamics, MOND, which is supposed to explain the observed rotation curves without the aid of so-called dark matter. Milgrom also established that this value corresponds approximately to the quotient of the speed of light and 2 pi times universe age. That means exactly the quotient that was just derived as a constant acceleration inaccuracy. So I hope that I have now been able to show in this video that this numerical agreement is no mere coincidence. At the edge of galaxies, the stars do not rotate faster than predicted by Newton due to ominous dark matter around the galaxy center, but because the discrete orbital classes become increasingly coarse-grained, that means the orbital velocities can no longer be sufficiently accurate. And then there is dark energy. In other words, the phenomenon that galaxy clusters and superclusters obviously move away from each other faster and faster the further apart they are. This cosmic acceleration is also of the same order of magnitude as the value obtained by dividing the speed of light by the age of the universe. And if we imagine that the entire universe could be rotating, which recent analyses suggest from the unevenly distributed sense of rotation of many observed galaxies, then the distance between two distant galaxy clusters can be seen as the radius of a rotational motion, and the ever-increasing rotational speed is a direct consequence of the fundamental rotational acceleration inaccuracy. I think the crucial mistake that the academic physics community has made in recent decades is to see the scope of Heisenberg's uncertainty principle only in the subatomic range and the associated Kupf-Muller uncertainty principle only in the practical environment of signal processing. In my opinion, the application of these principles to the cosmic realm is the key to remedying the shortcomings of Newton's and Einstein's description of gravity, and to gaining a fundamental understanding of the cause of gravity.